Dockless electric scooter service in LA is drawing criticism because of unattended scooters taking space in the sidewalks and blocking building entrances. This may change the probability of the competitor doing business in the Chester city. Let P be the probability of the competitor starting the business in Chester city. Set up the expected value equation for each decision alternatives. Now this video is about sensitivity analysis. It is about how the decision analysis, especially the expectation value analysis, would change according to the change in probability. So in the previous video we solved these expectation values with 60% of chance of S1 and 40% chance of S2, but now the market is changing and the government might become less willing to allow these dockless electric scooters, so maybe this P, which was 60%, might go down. So let's say this P, I don't know what this probability is, P, the new probability is P. Then what's the probability for not having the competitor? Well, it would be not having something, it will be 1 minus the probability. So whenever you have a probability of one thing happening, the probability of that not happening is 1 minus P. So the expectation value for each is now computed with this P rather than a specific value, and it will end up becoming a function of P. So first, remember the expectation value is the sum of the outcome times the probability. So we do 5 times the probability is P plus 5 times, this time the probability is 1 minus P. That's 5P plus 5, multiplying like that. 5 times 1 is 5, 5 times negative P is negative 5P. 5P, 5P cancels and you get 5. Well, right now, somehow the P's canceled and you end up with a number that doesn't have anything to do with P. But that's a very special case. Usually, you're going to have the function, you're going to have the expectation value as a function of P. So let's think about this D2. In the decision 2 case, the outcome 3 has a probability of P, and outcome 9, having $9 million, has the probability of 1 minus P. And in that case, that's 3P minus 9, actually plus 9, 9 times 1 is 9, times 9 times negative P is negative 9P. And 3P and negative 9P are like terms. 3 minus 9 is negative 6, so you have 9 minus 6P. And as you can see, it does depend on P. EV D3 has negative 1 as a possible outcome with the probability P, plus 12 as the other possible outcome with probability 1 minus P. Multiply them. Negative 1 times P is negative P, plus 12 times 1 was 12. 12 times negative P is negative 12P. And negative P and negative 12P, these are like terms, and that's negative 13. So it's 12 minus 13P. Okay. Now, next question is draw the graph of expectation value equation for each decision alternative. So remember the equations were EV D1 was 5, EV D2 was 9 minus 6P, and EV D3 was 12 minus 13P. Now, the best way to draw the graph is to start with 0, and then see you have one axis for P. I can't draw a straight line here. Okay, so let's say this is your P. The other axis is the value of the profit. So that's the profit. Let's just say this is the EV axis. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It goes all the way up to 12. And for the x-axis, the p-axis, it's good to get 10 of them. So it is 0, 0.1, 0.2, 0.3, 0.4, 0.5. This is 0.5. 6, 7, 8, 9, 10. So this is 1.0. So for these EV equation graphs, it's good to have your axis labeled from 0 until 1.0 with 0.1 as your spacing. And what you do is you plug in 0 and 1. See, these are all line equations. If you knew P is like X, so if you had the graph like Y equals to 9 minus 6X, what's that? That's a line equation with YX is 9 and then a slope negative 6. Now, once you know that these are line equations, then you can say this. Lines are determined by just 2 points. So if you know the value of this graph as 0 and 1, when P is 0 and P is 1, then you know the line. That's all you have to do. Okay, to demonstrate this, let's start with EVD2. That's the simplest thing to draw, I think. So EVD2, if you plug in 0, what do you get? 9 minus 6 times 0, that's 9. So when P is 0, EVD2 gives you 9. So here's the value of EVD2. Then you plug in 1 for P. If you plug in 1, 9 minus 6 times 1, that's 9 minus 6, which is 3. So at 1, you have 1, 2, 3. And once you know that EVD2 is a straight line, then all you have to do is just connect these two by a straight line. Okay. Let me try to draw a straight line here. Okay. So you start from here. Connect this. And then let's see. Let me try this again. Start from, because I want to be exact. Let's see. Start from this point, then you end up until, I think I should be using the mouse. Okay. Oh, okay, I can drag this. Okay. All right. Format shape. I want to make it thicker. All right, that's good. All right. Okay. Now let's start with, then let's move on to D1. See, EVD1, that gives you 5 regardless of whether P is 0 or P is 1. So it's a graph from 5 to 5. It's a straight line. Okay. Let me change the color. Maybe green. Okay. All right. Now for EVD3, when you plug in 0, you get 12. So I need to get 12. And then when you plug in 1, 12 minus 13, that's negative 1. So it goes all the way to negative 1. Let me change the color again. Yeah. Okay, good. All right, so these are the graphs of the probabilities. Now, what's important here is that for different probabilities, you want to decide using the EV expectation values, right? So what you're going to do is, let me use this. When your probability is between 0 to somewhere here, I don't know exactly what that is, you're going to go with D1. You would try to have 40% increase. That's actually, this was D3. I should actually label these. This is D3, this was D2, and this was D1, right? So you're going to have 40% increase if your probability is below some certain point. And then between here to there, this blue line is the highest among the three lines, right? So between here, you go with this blue line. And then lastly, when the probability is above certain point, you're going to go with the green line, which is D1. So there are some intervals of probabilities where D3 is the most effective decision, and there's another interval of probability where D2 is the most effective decision, and there's still another interval of probability where D1 is the most effective decision. Now, to actually know exactly what spot this is, you're going to have to figure out these intersection points. So let's try to find these intersection points. First, what's the intersection between D3 and D2? So we want to find the intersection between those two. To find the intersections, you set them equal to each other. And therefore you get 7p equals to 3. So p is equal to 3 divided by 7. So this point here is 3 over 7. On the other hand, to get this point, you need to find the intersection between D2 and D1. So you take D2 and D1, you're trying to find the intersection between these two. Again, you set them equal to each other. Now, add 6p both sides, so 6p is brought over here, and then subtract 5 both sides. So on the other side, you get 9 minus 5, which is 4. Dividing by 6, you get p equals to 4 divided by 6. And because they're both even, divide top and bottom by 2, and you get 2 over 3. So 2/3. So here is what you should do. If your probability cannot be less than 0. Probability is always between 0 and 1. If your probability is between 0 up till 3/7, you go with D3, because D3 is the highest, right? If your probability is between 3/7 up till 2/3, then you go with D2. And if your probability is between 2/3, probably cannot be more than 1, so the maximum can be as 1. In that case, you go with D1. Now, this actually is a result that includes our previous analysis, where it said if the probability was 0.6, if the competitor appearing there was 60% chance of competitor appearing, we should go with D2. Now look here, this is about 0.58 and this is 0.66, so this is between 58% to 66%, and 60% definitely belongs between these two, and in that case it's D2. So even if the probability changes from 60%, if it's decreased by slightly, you should still go with D2, but once it falls below 3/7, which is like 58 or 57%, then you should change your strategy and go with D3. So that's what probability sensitivity analysis does. Such an analysis is called the sensitivity activity analysis.